So last week and 2 days ago, we started to look into the torque and speed characteristic. So we basically using the basic formulation like this voltage equation together with the torque equation. We can therefore derive equation 11, which is the speed to the torque correlation. So this is a really famous correlation. You can see the equation only controlled by the input voltage and also the RA, armature resistance. So if these two are constant, then we can actually get the correlation between omega and the torque. So from there, we can see that the equation really look like a linear equation, like y equal to c plus mx. So that's to say, you can see that the equation here, the slope will be equal to this constant m1 here, which is this constant, only controlled by the RA, and also the flux. You can also see that RA will be related to the parameter for the motor. So once the motor is fixed, then the slope could be fixed. Unless in here we use the flux control, because some motor we are using separate flux control. In this case, we are able to vary the slope. So if we're able to vary the slope, you can see that when we increase the speed from this point to that point, then we find that the output torque will become lower. Or if you want to have a more gradient, for instance, sometimes we want to have a little bit of the torque being able to control the speed, then we do adjust this too. So that is to say, you can see that the flux actually are quite important to control the variation between the speed and the torque. So if we can see that if we increase the amount of the flux to the motor, when this is large, then slope will become lower. Then in this case, you can see that the speed will be more constant, even though when we change the torque. That is to say, when the low torque being changed, for instance, a machine or electric vehicle, whatever, when we want to speed up overtaking something, then we need to increase the torque quickly. Yeah. Then in this case, usually for motor control, we don't prefer the speed to change that much because we like to have more constant speed operation. So that is to say, you can see that the only thing we can make the motor become more stable will be try to control the metal flux. If the metal flux can be large, then in this case, then the whole slope here will be more horizontal, more linear. In this case, the speed will be quite independent of the torque. So it's something we observe that, for instance, this phenomenon, we can see that if we got a power supply, for instance, or we have a battery. If we draw more current from the battery, the voltage will drop. Of course, we want more stable voltage, even though when we change any current, change the load. So that means in order to make the battery become more stable, then that is also similar to here about the gradient. Another parameter you can see that is RA, the internal resistance. So you can see that if these are getting smaller, then the slope will be more horizontal, smaller. Yeah. Then when the slope is lower, then we can therefore make the whole line become more horizontal. So that's similar to the case because RA is internal resistance. So this is the losses. So in this case, if we're able to control the flux to be more linear, then in this case more constant, then we can able to have less dependence between the speed and the torque. For all the motor drive systems, we do prefer the speed will be quite independent from the load. When we have high demand of the load, that means the torque variation, the speed usually also be changed, but we don't quite like that. So that means if the M can become smaller, then in this case, it will become less dependent. So the C1 here is the intercept here is the voltage related to the voltage. So in theory, we can able to also use the voltage. This term, we can therefore increase the speed. And also in here, we can also decrease the flux here to increase the speed. So there's some phenomenon in here. For instance, if a vehicle in the standstill, you will really need a large torque to operate. Then when the vehicle go to very high speed, for instance, in the highway, they go up to 100 km per hour, maybe even higher than that. Then you find that actually the frictional torque for the vehicle are less because at high speed, the roller resistance for the vehicle will be lower. Of course, when you go to a very extremely high speed, there will be higher resistance due to the air resistance. But so that is to say, if you want to increase the speed further, besides increase the voltage, but however, power supply, you have the limitation of voltage. You also limitation for the winding voltage rating. You can't increase the voltage indefinitely. Yeah. You also have the core loss. You know that the core loss are proportional voltage. The transformer or the motor have an internal magnetic core. So that means once the voltage goes to an upper limit, then you cannot increase the speed further. Even though you decrease the torque to really small, that will be limitation for the maximum speed. Do you get my point? So this simple characteristic, we can observe a number of things. So when the high speed operation, then the motor torque will getting lower because in high speed, then we don't need to worry too much about the starting torque or the low speed friction. Then, however, the top speed here are actually controlled by the voltage, the input voltage. And then, for instance, if our electric vehicle or our train, whatever, the voltage is 800 volt. Then of course, whatever we do to control the maximum voltage I can apply to the motor will be 800. So that will give you the upper limit for the upper speed. So that's quite reasonable, right? And then, however, there's one more thing we can do further to increase the speed. What do you think? When the voltage goes to upper limit, then that's it, right? Can we do anything further according to T equation? If you done anything motor control, you may have known that concept. What is the question like other than this? In this torque speed equation here, right? This C1 is the y-intercept. Yes, this problem. So this the height here or the parameter here are equal to input voltage divided by the torque constant and phi. Torque constant K is fixed, cannot be changed. Once the voltage given. Only two parameters can change the input voltage. If the motor controlled by PM or some constant flux control, then the only voltage can vary. But you can increase the voltage to increase the speed, but there will be limitation. Because when the voltage increase to the maximum voltage from your vehicle, maybe from your motor, from your power source, that will fix it. For instance, your electric vehicle uses 800 volt. The maximum voltage you get use 800. You can chop it into low voltage. You can use voltage control at low voltage, maybe high voltage, but that will be upper limit. Depend on your power electronic. Once your power electronic reach that upper limit, you can't do anything further. Or when your motor winding cannot increase its voltage indefinitely because the motor winding have a limitation. High voltage will have breakdown of the winding. So V-in will have a limitation anyway. So once you reach the maximum for your system rating, you can't do anything further, right? But what can you do? Have you heard about that?
We can change the flux.
Yeah, you can change the flux. So in here, usually the flux here, we use the best performance of the flux. For example, if a PM machine, that the flux will be fixed. If we use a coil in here, then the flux will be usually fixed. But when the motor go to the top speed, if you like to go even higher, There's some technique, we call it field weakening. I think you heard about that. Field weakening.
Will decrease the flux.
Decrease the flux, yeah. That is called the field. There's a really famous technique we have been used, field weakening. We'll discuss that further. So the field weakening means we have operation normal flux. But when the motor goes to a top speed, we want to overdrive the motor. The only thing we can do is to weaken the field so that we can further increase the speed.
But if you reduce the flux, then the M1 becomes higher again, right?
Yeah, I'm going to look into that. Yeah. So so in this, so you can see that in this intercept, then we are able to increase the speed further. So you can see the whole curve will moving upward if we decrease the flux. The next thing to see will be about the torque. What you say is right. You can see here, when we decrease this one, the slope will become smaller, right? Much smaller. Then you can say, oh, that is smaller, then this will become lower, right, in freeway. But that one thing is, you can see that this negative. And also what we're talking about here, the torque here will be when the vehicle overdrive with really high speed, then we don't have any static friction. We only have the roller resistance. So actual frictional force at high speed will be much lower than the static. So the torque here will be less demanding, much lower. Just like when you drive your vehicle, in the first gear, then you find that will be a lot of friction because at low speed, you have a lot of the frictional force. But when you go to fifth gear or high speed, D1, D2 drive, then you can see the vehicle have less friction. Yeah. That's why you can use high gear. High gear means we have less force, less torque, right? Low gear, you got more force, more torque. Why is that? Because in high gear, when high speed, the vehicle can use less torque to operate the vehicle. So that's a common thing we can see that although the torque speed characteristic is really simple, but we can see that we are able to use the so-called field weakening to increase the C1 term here. So that's one of the key operation for field weakening of operation. Later, I will show you more curve about the implication of this motor operation. Have you heard about the term called the field weakening for motor? Okay. That's really important concept. I think in the next week, we'll show you this new concept, not really new concept. It's really basic concept for all the motor drive system. Any question up to this point? So you can also see the M1 term here is all controlled by the slope about the gradient in here. So that's why you can also have a lot of the issue. We can look into that. Anyway. So this curve basically you show us the voltage performance. And then we are able to look in order, instead of voltage, the next scale we can use is so-called the field weakening to weaken it. So another characteristic we can see will be like that. So this curve, when the torque equal to 0, then of course that will become omega directly proportional voltage. So at this point here, we have 0 input voltage, we have 0 speed here. But when we increase the voltage, you can therefore increase the speed further in such a way. But however, when we start to have a higher value of torque, then this portion will start to decrease the speed from this curve. So that's why I can see that when Tm increased, then we will have a decrement in here. So the curve will move in such a way. So you can see that there's a number of things we can work on here. For instance, when we have a constant voltage, like in this point, if you draw the vertical line in here, then you can therefore see the variation of the torque relate to the speed. Yeah. So if we want to increase the speed, we must decrease the torque and vice versa. Or if the torque is a constant, like this term become a constant in here, then we can therefore increase the voltage to increase the speed. So the curve will be quite simple and straightforward, but we are able to observe a number of the control phenomenon in here by using by correlating the voltage, speed, and also the flux to work on.
T is increasing, being like, is increasing which way?
T is this arrow, yeah. This arrow. When T increasing, then this term become larger, the whole term become subtract more. So that means the speed will getting lower. Yeah. So when this line is equal to 0, when we have larger Tm, so the curve are moving downward, more in this direction, because we subtract more from there. So that is to say, in theory, that's quite sensible. When the torque become really, really large, then of course the speed must be lower and lower until it vanishes. Yeah. But only thing we can do will be further increase the voltage. But of course, there will be upper limit for the voltage due to the voltage rating. So there's many ways we can manipulate with the curve, but it all depends on which one we want to keep it as a control parameter, which one will be fixed parameter. Okay. So after we finish this curve discussion, let's do a quick tutorial, and then we discuss the answer. So we have DC motor connect with a variable DC source, and the armature resistance is 1.5 ohm, the combined motor constant. I combine these two together because this anyway is a constant, we are given motor, unless I'm going to change the flux. And the armature current, we try to have a controller, control 2 amps. And then now we do calculate the motor speed and motor torque at 15 volt. Next is to calculate again the torque and speed, but now at 20 volt. So calculate both cases, and then you need to tell me which one have higher efficiency. Okay. Have a quick think about the question, and I'll give you 1 minute to try it before you look at the answer. Have a quick look.
So you are asking which has higher efficiency?
Yeah. Of course, before you calculate, you should know
Main
about that.
equal to 15 volt and higher efficiency.
Yeah, you say 15 volt high efficiency.
Yeah.
Okay, later on, you have a quick calculator, get a paper. So quick calculation, then we look into that. Okay, I don't like you to just look at the answer, right? Have a quick try it. Although it's really simple question, but do try it, yeah.
Twenty-one and higher,
Yeah, 21 high.
85%.
Yeah, yeah.
So, yeah.
Of course, we have that calculation, but of course, one of the comment will be explain how do you see that observation? What's the physical meaning for that? That's most important. As an engineer, we need to know its physical meaning rather than just from number.
So higher the voltage.
Why we have high efficiency? Why? You can't just say, oh, because of this calculation, tell me 20 volt high efficiency. That's not a good answer. You need to tell me why 20 volt, what kind of physical phenomenon will give you higher efficiency. That is the thing I like from you.
So the percentage of loss, when when the input voltage is higher, yes.
Yeah, we got two cases. Case A will be when input voltage equal to 15 volt. Case B is when input voltage equal to 20. And then in both cases, you need to calculate speed and the motor torque. And then you also need to think about the efficiency. Which one have high efficiency? That means you need to calculate efficiency for case A and B, and then compare them to see which one is better. And then tell me why.
The current is the same.
The current we say they all control at 2 amp.
Yes, that's mean the power dissipation boundary heat is the same. And they just distribute 3 volts. So if we have a higher input voltage, that means that the more voltage will apply in the electrical machine. So it has a more efficiency because the same current.
Something like that. You need to tell me a little bit deeper in that knowledge. But anyway, let's go through the answer first, right? The
Higher
answer,
power, higher.
now usually high voltage will be high efficiency. For most of application, we usually have so-called the standalone losses or so-called the standard losses. That will always there, no matter how you operate. So, but however, you have high input voltage, you can physically, you can make that standalone losses or will be have a less portion. So that's why you have high efficiency. And then in this case as well, we control current at 2 amp. We got a constant resistance for the armature. So the losses in the armature resistance will be fixed. So, and then you can see the motor. The only losses in the motor, of course, we do not mention anything about the resistance, the friction. The only loss will be electrical loss, I square R losses in the RA. So if this loss is fixed, then the remaining will be all go to the output power. So when we have the high input voltage, we will have, according to the equation here, you got higher speed, right? High voltage, you got high speed, that means higher output power. The current is proportional to the torque anyway. So supposedly the torque will be the same, but the current is higher, we got higher output power. Now that we got higher output power, a higher voltage, but we only have a fixed power losses. So of course, high voltage, we have higher efficiency. So that's the concept we try to present in here. So now then we come to here. Now use the equation, voltage equation, input voltage 15 volt, and then the work drop IARA 2M times 1.5, and then we can calculate the speed from the back EMF, which is 120 radian per second. So this SI unit. So of course, for user point of view, they don't understand radian per second, they only understand RPM. So we just change them in RPM, become 1145. And then the torque here will be equal to the torque constant multiplied by current equal 0.2 Newton meter. And then because we need to compare the efficiency, we first calculate efficiency here, then output power divided by input power. We have formulation, right? EA over EA plus IARA, which now we got 80%. So in here, the output has been decreased by the losses component in here, right? So 15 minus 2 times 1.5. Because EA is equal to this voltage minus this term, right? So that's why I got 80% anyway. So very simple, straightforward, only from voltage equation. Secondly, we will now increase the 20 volt. So 20 volt, and then now the work drop also unchanged. 2 times 1.5. Now because it's unchanged, we got higher voltage, so back EMF will become higher. We got higher energy go to the motor. So now we got 170 radian per second. In RPM is this. Obviously, we got high output power now. So the efficiency must be better. So the torque is now unchanged. Only the speed have changed. The total output power still increased. So the efficiency is now become 85. So before was 80, but now become 85. So obviously the efficiency for 20 volt is higher. And then we usually ask you about the physical phenomenon. What's observation? Why is that? So don't just give me the answer because of the A and B comparison, 85 and 80. That's not a good answer. Similarly, when you're writing a journal paper, you need to tell some physical phenomenon. When you compare some experimental result, this and that. When you do the benchmarking, usually when you write your research paper, your last section, so-called the benchmarking. Benchmarking, I think all of you know. Benchmarking means you need to compare the performance of your experiment, of your research with other user. And then you say why yours is better. Then you need to tell them the physical meaning about this. So in here, we have written down here, the armature remain unchanged. So the voltage applied to RA remain unchanged. So that's loss component. So that means we got consistent loss component. If the loss is unchanged, now then when we apply input voltage, the back EMF, of course, will increase. What's the back EMF? The back EMF is the one deliver the output to give you the output energy, output power. So that's why we will therefore give you an increase in the output power. Loss is fixed. When you increase the voltage, you got high output. Of course, your efficiency will be higher. So that's the physical meaning of how we deal with the benchmarking, how to compare with other counterpart, and then explain to the reviewer or user why we have higher power. Okay? I think you did that. When you written any research paper, you read that section, right? So remove. So I think you did that, right? So that's how we look into all this. So next will be the field circuitry. Just now we assume that the motor will have another field circuit, and then the motor, all the DC motor require magnetic field. This magnetic field can be have different way to go into the motor. We do have a PM motor, permanent magnet. So that's a really basic one. The first time when we developed the motor 200 years ago, this is also a PM motor. And then we have basically 4 different types. Separate excited, that means the motor field winding are separately applied to the motor. So we have separate winding provide the magnetic flux. So in this case, you can see that we are able to independently control the field by using another coil. And then we also independently control the armature current, because armature current only using an input voltage applied to the armature. However, that will require 2 separate circuitry. And then people were talking about, why don't we put this field winding in series with the motor? We can reduce the power source. In here, you can see that we need 2 power sources. But now we only need 1 power source to connect to both field circuit and armature circuit. And then since we can connect them in series, why don't we connect in parallel? So now then the field armature are connected in parallel. But these two do have some pros and cons. It's not perfect. So that's why we do another one to combine these 2 together, become the combined mode, combined DC motor, which look like a hybrid version of series and shunt. So basically, you can see there's a 4 possibility for the motor connection. They all have their own pros and cons. So let's look at the first one. The first one is also very common, especially here you can see the armature, we are independent to control the armature here. You can adjust the voltage, therefore you can control this current IA without any restriction. And then we also independently control the field. So this method is good because we can adjust any field current. That is to say the field current usually proportional to the magnetic flux. So that means we can able to use normal flux, optimum rate of flux, or sometimes we can use field weakening quite easily. Especially when you overdrive the motor, you can use field weakening to further increase the speed. If the field winding are connected with other circuitry, we have less flexibility. So DC motor is something really good. You can control the field independently, like this case. Then we can control the field weakening, control the speed really, really well. But armature IA are controlled with the IA related to the top. So that means in here, so IA here is related to the motor torque. So you can therefore, the torque here are being controlled directly by using input circuitry here. You can just adjust this voltage or some input current, you can control the torque. And then in here, we can control the field, which although the field also relate to the torque, but you can adjust the field to any parameter. You can also do with the field weakening. So that's why this kind of DC motor is really preferable by many users, because we so-called independent control of the field and the armature. So we call the two, we call independent control of this and independent control of this. Yeah. If you see if a motor, you can independently control its torque. So that means in case you want to suddenly within a millisecond to increase the torque rapidly, then you can just adjust the input current or input voltage here and keep the field become unchanged. So that's really good. And then if suddenly you want to use the field weakening, then you can quickly to reduce the input voltage. So that's why this kind of the separate control is one of the best methods for DC motor. Control capability is really good. But of course, the disadvantage will be we need two input source, two control circuitry. So of course, there will be pros and cons. We don't have perfect. So for many AC motor, we don't have that good control capability. You see, AC motor are using sine wave. So we need to convert the sine wave voltage into something we can control the motor torque and motor field. That will be really difficult, impossible, unless we use the vector control, which we developed about 25 years ago, and then we use vector control to control the motor, AC motor. But before vector control, we have really difficulty to control the induction motor or AC motor. But we always like to control induction motor, like what we control DC motor. Everybody happy about DC motor because we are able to control IA and IF independently. So that is the picture why we like separate excited DC motor. Another one will be also quite very interesting. In order to reduce the power source, sometimes two power source is really expensive, more control, then we put them in series in this case. So series DC motor is also very common, a lot of the application too. So obviously you can see that we connect the two current, that means IA equal to IF. The two current are equal now. So what do you think about this motor? Of course, you can see my looks here, right? And you can know what's the pros and cons, right? But how about you think about that? Why this motor is useful? In what condition will be more useful? What kind of the application are mostly suitable for series type?
First thing first, we need just one source.
One source. Now, obviously, you can say I can reduce the cost. I only use one source instead of two sources. Then besides, you can save the equipment, save the power source. What else will be suitable? You can see that if you use the motor for some expensive application, if the people don't care about one source or two sources. So what do you think?
Washing machine.
What machine?
Washing machine.
Washing machine.
It has high starting torque. So washing machine needs the high starting torque.
Well, if I say high starting torque, this motor especially have high starting torque than others, than the Shunt or than the others. So that means application require high starting torque will be advantageous. And also for washing machine, probably you want to reduce the cost. You don't want too many power sources, right? That's one of the good example. Another example will be for train. Actually, in the old day when we have the electric train, the people tend to use series motor. For train application, especially in the train is so long, many coaches, many cars, right? So that means the starting torque, we need to provide so high force, so high power to move the train from standstill. So the starting torque for train is much, much higher than washing machine. So that means this motor are capable to do that. So why this motor will have high starting torque? Anybody can tell me?
Inductor.
Which inductor?
When the starting, we put the input voltage, the current in the inductor will increase, but because the characteristic of inductor, it will produce some voltage across this whole path. So finally, we can have the formula like that. So just like the EA will decrease, so the torque will increase.
Okay. Any other explanation? Any other comment?
Because we see the input voltage is equal to field circuit voltage plus
Mm.
armature voltage,
Yeah.
which gives you high voltage, which means high torque.
Mm. Obviously, when the motor just started, then the EA here, because proportional speed, so that will equal to close to zero anyway. So that means all the voltage input voltage applied to the IARA plus the field here. Then, of course, in this case, the current will be really large. The starting current must be really, really large. We want to be large, so that firstly, we're able to have a high torque because torque is directly proportional to IA. So this motor will obviously have a high torque parameter. And the next thing you see, how about the field? Would there be an issue for high IF during the starting? Then you can see that from the equation here, when the initial field current also become large, yeah, because when we have a zero back EMF, so field current large, that means the flux will also become large. Then from this equation, you see that this will usually starting will become quite large anyway. Quite large here, then that means the whole thing here will therefore become in here become much
Smaller.
smaller. But we don't because it's starting we don't need high speed. We want low speed anyway, so it doesn't bother us. So that is to say, for the series connection, we know the starting speed must be small, but we're able to provide high starting torque. The torque is so high, which this one virtually go to zero. We got all the current applied for the field and also armature. We're able to have really high starting torque. So that's the reason this motor has been used in the initial design for the train. For train is really high force. So but of course, so that means still many trains, they're still using DC motor because starting torque really high. And gradually, about 20 years ago, then we started to move on to industrial motor, AC motor. But of course, we need a good technique for the torque control. AC motor torque control is really complicated. So we need better technology, which only developed about 30 to 25 years ago. Anyway, so this motor also really robust, and because we don't have that many connections, we want a single power source, so usually less component will be better advantage in terms of the robustness. So the speed control also really good, but of course the actual speed regulation in here. Then because we need, if you want to use a
Is that low speed and high torque, right?
low speed, yeah, is my typo here. Low speed and high torque. Low speed. So let me get my pen. Where's my pen? Oh, here. And the speed regulation is poor. Why is that? Why the speed regulation is poor?
Yeah, in separate one, we had that variable we can easily regulate. Here, everything is in series, so
Yeah. Obviously, you cannot independently control the field current because field current are being shared by the armature current.
Yeah.
Armature current, we usually tend to use it for the torque control. When you want to control the torque, you tend to use the current to control it. And then once you control them, then for instance, you want high torque, you need a high IA. And then high IA, you get high field. High field, that means you cannot have field weakening. So that means in high speed, when you go to a high level torque, then you have difficulty to regulate the torque and the field together. because both of them need to increase simultaneously. That's not the way we control motor. So that means for the speed regulation, that is not a good way to do that.
Being all
So how they used to do that at that time to control the speed?
The best way to do will be this one, the separate control. This one, only we do have a difficulty to have a detailed, really good control for the speed because mainly about
So
armature
this
current
series they were using in the train
in the train, yeah,
in the old days.
in the old day,
How
but
do
not
you
anymore.
control the speed thing? So
You can still control the speed really well. Because high starting, you can still control the speed really well, but you have really detailed, really good positioning control or rotational control, it's not doing really well. What I meant is it's still able to control the speed, but however, for really detailed speed control, it's not this type of the motor.
so because we increase the V, but in this case, the flux will increase those. So we cannot control like the formula V divide K times.
That's true, yeah.
But that is also if we increase the V, we also will increase the flux and IA. So like the times, so the torque will very large. Is that cos equals K times flux times IA?
And when you increase the input voltage,
Yeah,
then all these things could be increased depending on that.
yeah.
And the EA here will be mainly proportional by the speed. So when you have higher speed, then this need to be increased anyway. Then you got less voltage on this field and here. Then if you want to change the speed, that means this term will also need to be changed. The only thing you can change this term will be using the current, adjust the current, or adjust the field. In this, how to adjust, you need to adjust the voltage. So that means you have difficulty to use this voltage, in voltage, to adjust all these three terms together. Yeah, but in this case, you have separate control for VA and VF. You can do whatever you like. So we can still control it, but this has some limitation because they all correlate to each other. That's the reasoning I say the difficulty to have good speed control. So of course, next one will be the shunt DC motor. Shunt DC motor also pretty good because we are able to parallel the two circuitry together in such a way. So probably when you have fixed input voltage, it's quite common. All the electric vehicle machine, they use a fixed input voltage. But in here, we are able to have in the separate regulator to control the field current. For instance, I can have a potential divider or any power electronic here to control the field without any difficulty. Because these two currents are separately controlled anyway, although we're using the single input voltage. So that means the good thing, obviously, will be we only need a single power source. Speed regulation is good because we are independently control these two. Yeah. If you want to increase the current here, you need to regulate the input voltage. Once you regulate input voltage, you may have inconsistent field current here. You need to change that resistance. So we can change something. So the speed regulation is much better than previously because we got additional resistance here to control the field. But the disadvantage here will be the starting torque may not be as good as before. So why the starting torque is not as good as the previous case?
previously, like EA was 0. There, you cannot. There's 0, right?
Yeah. Of course, when all the motor usually starting torque are really good because this one equals 0. We got high current anyway. So usually the motor have a better torque anyway. But however, if you look at the field circuit here, then the torque for the torque here depend on the current. This is large, right? So it also torque also proportional to the flux. This flux is controlled by the field circuitry. So simultaneously, you also need to apply high flux to the torque equation. So where this come from? Come from the field circuit, which come from here, right? So that means if you want to, for this circuitry, you want to have high starting torque. Besides apply high input voltage here, you also make sure that this current also be large in order to do that. So that means you need to control both of them together, make sure the torque will be reasonably high. But however, when this voltage is fixed, usually you want the field circuitry, don't need the high voltage because the field circuit will be using less current. So if you tend to use high voltage in here, but the field circuit, you don't need the high voltage. So the deliberately apply high voltage, so you need to use high resistance variation here. Once you use high resistance here, in the later on, if you working at lower torque, then you need to decrease the flux here. Then in this case, the flexibility of this will be less. So because in here, your RF here actually try to program with the different domain of the flux control. So that's why for this circuitry, the high starting torque, we need to invest more in the field circuitry to do the job. It's not that easy to do that. And also the input circuitry here is not in series, both of them. So the starting current in here will be limited by these two components. But here the starting current is not being limited, can be really, really high, can be infinity, not infinity, can be really high because once this becomes zero, all the current pass through here. So then that will be really high starting current. But here the starting current is also sensible because it's series with the field circuitry and also the armature resistance. So that means our series and also the shunt do have some advantage, disadvantage. So usually people will try to work on a combination of both of them. So that means the shunt and series in such a way. So you can see that in here, the input voltage can pass through a series mode connection to the armature. And then they also parallel with another field winding. So we now combine these two together. So we can adjust both of the circuitry in order to control it. So in this case, we're able to take the advantage. When we design them, we take the advantage for both cases. Then we can be able to regulate its performance, including we're able to adjust higher torque. Another thing will be run-away. Anybody tell me what is the run-away speed? Have you heard about that? You heard about thermal runaway, right?
Yes.
What's the meaning of thermal runaway?
When it heated up and due to short circuit, some kind of thing.
Anyway, thermal runaway means suddenly some temperature cause the component or equipment
The short
become
circuit.
chaos. Then means so high temperature become suddenly malfunctioning, then disaster, sort of. They mean uncontrollable. Uncontrollable temperature, uncontrollable the runaway. So in here, the runaway speed mean
Start
The-
0 and speed.
the speed of the motor suddenly go haywire, go to really high speed. This could be quite dangerous. The torque cannot be runaway torque. The torque will be fixed by the input voltage, by the input current, unless your short circuit, right? But of course, when the initial motor start, we may have high starting torque, but the speed is limited. No matter high torque you have, the torque only use it to accelerate the motor. And then you can see in here, so the torque usually don't have runaway torque, but we have runaway speed means suddenly the speed will go to haywire, go to very high speed. So what condition of motor can go to runaway speed? Suddenly speed originally would 1,000 RPM, suddenly become 10,000 RPM. Then such high speed will make the motor become quite dangerous. The bearing will be a problem, the shaft may have problem, and the rotor will have problem. Suddenly the vehicle will become so high speed you can't control it. For instance, when you drive a vehicle, suddenly the motor speed go up by double or 3 times, then you will be frightened. Yeah. So what condition will give you the runaway, speed runaway? So you can look at the equation here. If suddenly the thrust will become lower, then I think you remember, we have something called the field weakening. So when the motor have certain voltage, the EA will roughly about constant. Don't change that much because the EA voltage are controlled by the input voltage. Input voltage from the battery for vehicle or maybe from power source 120 volt, that will be more constant anyway. You can't increase the voltage indefinitely. We don't have thermal runaway voltage. Because voltage controlled by the battery or controlled by input power voltage. So this more or less have an upper limit. And then the resistance here also have a fixed component. And the current usually you don't have infinity current anyway. So this voltage more or less have a certain parameter. So now that if you look at this voltage, then for certain amount of thrust, you're able to a certain amount of speed. You see one instant, suddenly you decrease the thrust by mistake or by anything. Then the back EMF unchanged, then the omega will be suddenly become very large. Then that's what we call runaway, speed runaway. So when on in the circuitry, suddenly accidentally or by any control issue, you suddenly decrease the thrust. Then the motor will momentarily have a really high speed that will so-called haywire, cause you a big problem in motor control. So because bring it directly from the back EMF. So you can't using controller to control it. The only way you can control the motor speed will be you are using the voltage, but that will be too slow. Before you use voltage control, the back EMF here already cause you the speed overdrive. So that is the field situation. So that means in this case, you can see that in here. Firstly, we are independently to control the shunt circuitry. So this will be usually the current will be come from the input voltage and this resistance, and also that field will be controllable. You won't suddenly become zero amount of the current here or a really small current. So the thrust here will be more or less won't be too far away from your nominal value. And then which one may have the runaway? Which one may easier have the runaway speed?
Series?
Yeah, do you think series will have runaway speed in some condition?
Yeah, because
What condition for this motor will have speed runaway? That means suddenly the
flux is like decreases, right?
suddenly we decrease the thrust.
But it is serious. The thrust will compact with
The top
high-
current.
Yeah.
Yeah.
So maybe it's difficult because when the IA increase,
Mm.
the flux also will increase.
But we are talking about is only a short duration. All this thermal run and wave only for short duration. It's not a continuous operation. Continuous operation, you control current, you control everything. You don't have any speed run away. Yeah, you think about that, and then you try to go to investigate which motor have high chance of the runway. Okay. So for this compound this motor, we also have the disadvantage like high cost because we need more control of the whole things in here. It got more complicated, and then that's why more complex and high cost. So that's one of the disadvantages. But this motor have firstly independent control IA and IF. So that's why we are also don't need to rely on the series connection in here. So that's why this motor do have a number of advantage. Of course, you invest more, then you do need to pay for more. Then of course, another one, PM is also quite a famous one because the PM is also separate control. We separate have a magnetic flux here to control on the motor. So in here, we got constant flux in here. And then in here, we also have controllable armature current. Then the armature voltage can be used to adjust the motor speed. And the torque here are only controlled by the armature voltage. So we do this kind of motor is also conventional. We are able to control the torque current really well by using input voltage. But of course, the flux here will be fixed. This term will be fixed. So that means the back EMF are only controlled by the speed. So that is to say, when this term is fixed, then you cannot have any field weakening. You can't momentarily to increase the speed further because that is fixed. So that is to say, for train application, if you use PM motor, we don't have any field weakening mode. So that means when the motor drive to the base speed, you want beyond the base speed, you want to further accelerate, then you cannot use field weakening. Field weakening mode is very important for many motor drive. So that means for this motor, we cannot, but people have been thinking about how to improve this permanent magnet motor by insert the field weakening. What they try to do will be put an additional coil in here to weaken the field during some overdrive condition. So you can also see some research paper working on that, try to additional coil. So the coil don't have to use. Only when you want to speed up the motor further beyond certain base speed, then you turn on that field winding to cancel out the field. The further you can reduce the field, actually, you can further increase the speed. So the same input voltage from the armature, then the speed, we can increase much, even though double the speed. But of course, the torque will be inversely proportional to the speed, and also probably will be the flux. So the torque getting much lower. But of course, in high speed, the torque may not be too important.
Can we do that by placing, here we have N and S, so we put S and N, but with low value, low magnetic value, but we change the S and N direction with less on like small S and N, but with a different angle, right? Instead of
This diagram will give you the thinking, but in fact, in the real motor, the PM are fixed. We cannot access that. And also you can see that the PM is quite fragile, quite brittle. I think you pay around some PM in the past. When the permanent drop on the ground, it break quite easily. So one of the key issue for DC motor, permanent DC motor, is the PM. How do you attach the PM to the stator? You know how you do that? These are PM, they got you think only 2 N and S, but actually these are we use a multiple slot, multiple hole, so what many of them in here. And then the thing is, we need to attach so many PM on the stator frame.
Yeah.
And the PM are really fragile. We cannot using screw or something. Many cases, we need to just glue them, super glue, this kind of thing. And then the air gap between the rotor and the here will be really little, talking about 1 millimeter. So any losing in the PM will cause collision, break the whole motor, crash. So don't think about PM motor so good because the PM is really really weak. Especially if PM you drop a few times, the glue may lose, then somehow that air gap will become a big problem. So if you want to adjust the angle so that you're able to make it different cosine theta here, you want to weaken the field, that would be even more dangerous. But however, the people put the additional coil around it, the key thing is you don't want to do anything with the PM. The PM is really weak. You don't want to touch that. PM motor, after you use for a few years, the glue will loosen a little bit. Sometimes the air gap will have some variation. So that means PM motor may be a good motor because it changes the environment. And the PM motor, after you use for quite a while, demagnetization may happen. You don't have that strong magnetic thrust. And also under temperature variation, like a vehicle, during the day, hot day could go up to 60 degrees. At night, it can be minus 20 degrees. Such a wide temperature variation will weaken the magnetic dipole there. So after a few years, then the magnetic field will lower. And also due to vibration collision, the magnetic dipole also become weakened. So it may be really good for a few years, the first year or first 2 years, but for this kind of high power application, then probably you cannot last for too long. But if you use copper winding, you don't have that problem. You don't have any environmental concern. I can see many of the PM motor actually crash, or some of the motor pole drop, because if you open up a PM, then you can see that internally will be some kind more look like powder iron. They have a lot of the dipole. They try to grind the dipole into really, really small powder. Why they want to use small powder? Because they're able to work at higher frequency of operation. Then they grind them, press them into the form, and then use something to contain them to fix the shape. So that to say internally, they are just look like the cement, but really weakened